Neptune's small inner moons look almost insignificant. Larissa and Galatea are tiny, irregular worlds orbiting close to the planet, while faint rings stretch between them. For decades, astronomers assumed these objects were probably just ordinary leftovers from Neptune's formation. But James Webb has now detected something on them that should not be there at all: minerals that normally require liquid water to form. That is strange for one simple reason. These moons are far too small and far too cold to have ever maintained liquid water near their surfaces. Webb also found no clear evidence of water ice in the spectra of Larissa, Galatea, Proteus, or Neptune's rings. Yet hidden in the infrared light was a strong signature of magnesium-rich phyllosilicates, a family of clay-like minerals produced by extensive interaction between rock and liquid water. So the clay probably did not form on the moons where Webb sees it today. It may have formed deep inside much larger worlds that no longer exist. And if that interpretation is correct, Neptune's current system of tiny moons may be the wreckage of a planetary-scale disaster that happened billions of years ago. The mystery begins with Triton. Triton is by far Neptune's largest moon. In fact, it contains more than 99% of the total mass orbiting Neptune in moons. But its orbit is bizarre. Triton moves around Neptune in the opposite direction to the planet's rotation, a retrograde orbit that strongly suggests it did not form together with Neptune. The leading explanation is that Triton began as an object in the Kuiper belt and was later captured by Neptune's gravity. That capture would not have been gentle. Before Triton arrived, Neptune may have possessed a more conventional system of large icy moons, perhaps resembling the major moons of Uranus. Then Triton entered the system on an unstable orbit. Its gravity could have thrown some moons outward, driven others inward, and forced massive collisions between them. Over time, the original moon system may have been largely destroyed. Until now, that idea was based mainly on orbital dynamics. Neptune's present-day satellite system looks suspiciously different from those of Jupiter, Saturn, and Uranus, and Triton's retrograde orbit clearly points to a disruptive history. But direct chemical evidence from the destroyed moons themselves was extremely difficult to obtain. The surviving inner moons are tiny and faint, and they orbit very close to an enormously brighter Neptune. From Earth, separating their light from the planet is extremely difficult. James Webb changed that. Researchers use Webb's near-infrared spectrograph, or NER-SPEC, to observe Larissa, Galatea, Proteus, and Neptune's rings. Instead of simply taking pictures, NER-SPEC divided their infrared light into spectra. Different molecules and minerals absorb very specific wavelengths, leaving patterns that behave almost like chemical fingerprints. The researchers expected to find materials broadly similar to those seen elsewhere in the outer solar system. They did not. The spectra were unlike those of other known outer solar system bodies. All of the observed moons and rings displayed strong absorption associated with hydroxyl, or OH, around 3 micrometers. But Larissa, Galatea, and the rings also contained a particularly important feature at about 2.72 micrometers. That feature is diagnostic of magnesium-rich phyllosilicates. Phyllosilicates are sheet-like minerals that include many types of clay. On Earth and other rocky bodies, they commonly form when liquid water chemically alters silicate rock. This is not a process expected to happen on the surface of a tiny moon orbiting almost 4.5 billion kilometers from the Sun. Larissa is only a few hundred kilometers across. Galatea is even smaller. Bodies this size would lose internal heat relatively quickly and are not expected to sustain deep, long-lived reservoirs of liquid water capable of producing extensive alteration. That means the material probably came from somewhere else. The simplest possibility is that these tiny moons were built from fragments of larger ancient satellites. Imagine an early Neptune surrounded by several large icy worlds. Some could have been big enough for radioactive decay, accretional heat, and internal pressure to melt part of their water ice. Liquid water inside them would interact with rocky material, gradually producing clay minerals deep underground. Then Triton arrived. If Triton destabilized the system, collisions could have shattered those differentiated moons. Their icy outer layers could be lost, redistributed, or destroyed, while material from deeper inside was blasted into orbit. Some of that debris could later collide again and slowly reassemble. The tiny moons we see today may therefore not be original moons at all. They may be second-generation objects built from fragments of the interiors of destroyed first-generation moons. That would explain something else Webb found. There is surprisingly little obvious water ice. In the outer solar system, water ice is everywhere. It covers many moons of Saturn and Uranus, and it appears on numerous Kuiper Belt objects. So finding clay minerals that require water while failing to detect clear water ice on these particular objects is deeply unusual. If Larissa and Galatea are assembled from deep interior debris rather than original outer crust, however, the contradiction begins to make sense. Their surfaces may be showing us material that was once buried beneath many kilometers of ice. In effect, Triton may have cracked ancient moons open and scattered their insides across Neptune's orbit. There is another possible explanation, and the researchers are careful not to claim the case is closed. The clay-rich material could instead come from a dwarf planet that passed too close to Neptune and was torn apart by tidal forces. If such a body had been internally altered by liquid water, its fragments could also have supplied the strange minerals now found in the rings and inner moons. But the destroyed moon scenario fits naturally with the existing evidence that Triton's capture dramatically rearranged Neptune's satellite system. The timing would have been early in solar system history, probably billions of years ago. Triton itself may originally have belonged to a binary pair in the Kuiper Belt. In one widely discussed capture scenario, Neptune disrupted that pair, ejecting one body while trapping Triton. The captured Triton would initially have followed a highly elongated orbit that repeatedly crossed the region where Neptune's original moons were located. Each close encounter could transfer enormous amounts of orbital energy. Some moons might have collided. Others might have been ejected entirely. Triton's orbit would gradually shrink and become more circular, eventually reaching the unusual retrograde orbit we see today. What remained behind would be a dramatically altered system. Today, Neptune has faint rings, several tiny inner moons, the dominant Triton, and unusual outer satellites. The architecture has always looked as if something violent happened there. Now Webb may have found the chemical residue of that violence. This result is especially important because scientists almost never get direct access to the interiors of large icy moons. Even when spacecraft fly close to worlds like Europa, Ganymede, Enceladus, or Titan, they mainly observe surfaces. Gravity measurements, magnetic fields, and thermal models can tell us what may exist underneath. But sampling material from hundreds of kilometers below the surface is another problem entirely. Neptune may have solved that problem through destruction. If Larissa, Galatea, and the rings really contain material excavated from ancient moon interiors, then these objects offer something unique, fragments of differentiated icy worlds that have already been broken open for us, that could reveal how large icy bodies chemically evolve when they contain internal liquid water. The mineralogy is particularly interesting because the magnesium-rich clays resemble materials produced by aqueous alteration elsewhere in the solar system, including some meteorites and material associated with Ceres. That similarity suggests that water-rock chemistry may follow broadly similar pathways even in very different regions of the solar system. But there is still a major unanswered question. Where did all the ice go? If these fragments really came from large icy satellites, those parent moons should have contained enormous amounts of water. Yet Webb did not detect the strong signatures of surface water ice expected on the present inner moons and rings. Some of the ice may have been preferentially removed during repeated collisions. Fine icy debris could have been destroyed, vaporized, or gradually lost from the inner system. Darker rocky material may have survived more efficiently. Another possibility is that the surfaces have been altered since the disruption, hiding the original ice beneath later coatings. At the moment, scientists do not know. That uncertainty is valuable because it gives future observations something very specific to test. More Webb spectroscopy could target additional moons and different parts of the rings. Laboratory experiments could also reproduce magnesium-rich phyllosilicates under pressure, temperature, and chemical conditions expected inside icy moons. If researchers can identify the exact minerals, they may eventually estimate how hot and how large Neptune's vanished moons once were. There is even another survivor that could help reconstruct the story. Nereid, one of Neptune's outer moons, has recently been investigated as a possible surviving regular satellite from Neptune's original system, rather than simply another captured object. If that interpretation holds, scientists may eventually combine the orbit and composition of Nereid with the strange chemistry of the inner moons to reconstruct what Neptune looked like before Triton arrived. That would transform Neptune from the least explored giant planet into the scene of one of the most dramatic events in solar system history. A captured Kuiper Belt world enters. An existing moon system becomes unstable. Large icy satellites collide and shatter. Their interiors are exposed. Fragments slowly reassemble into tiny moons and rings. And billions of years later, a telescope almost 1.5 million kilometers from Earth detects the minerals left behind. That is why Webb's discovery matters. The clay itself is only a chemical signature. It does not prove every detail of the catastrophic scenario, but it tells us that the material covering parts of Neptune's inner system experienced liquid water alteration somewhere in its past. Under conditions these tiny moons could not plausibly create themselves. Something larger had to exist. Something had to break it apart. And Triton, the enormous moon still orbiting Neptune backward today, may be the reason almost none of those ancient worlds survived.